This is John Black, super chemist, and the two aldehydes I want to start with are the easy ones, methanol and ethanol, which most people call formaldehyde and acetaldehyde. Now I'm going to start with the acetaldehyde because it's a liquid at anything less than 20 C. Here's the boiling point with the condensation point. So that's like room temperature, so I can cool it down to, ice is zero C. Formaldehyde is, you can't, it's a gas. So obviously I'm going to go with the one that I can liquefy. This is my apparatus here. What I'm going to do is, this is a dehydrogenation reaction. It's very endothermic, so it needs a lot of heat to keep it going. Basically, you just pass ethanol, over a catalyst like copper oxide, and it will oxidize it to the aldehyde, which is acetaldehyde. You can see here's the boiling flask. I would, just like I was distilling it, right? I'd heat this up. We'll come up here. Here's my thermometer. Now I have it set up here like a fish tank. You have an air pump that pumps air into it so the fish can get oxygen in the water. I'm going to use one of those to help circulate it, the vapors through, and also to help oxidize the copper into copper oxide. So it'll have airflow pushing, coming out. And you can see this tube here would be fused quartz glass. So that's a special kind of glass. It can really take the thermal heat. I'll put in the copper inside here, and when the vapors come up from the ethanol and the oxygen, I will heat it to 260 to 290 C. Then when the vapors come by, the copper will turn into copper oxide. That will in turn oxidize the ethanol into acetaldehyde. And you see it comes up here, and the product should come up through here and condense, because here it says 0 degrees on this water-cooled condenser. This water-cooled condenser is at 30 C. And if you notice, the ethanol boils at 80 almost, 78 degrees, and the acetaldehyde at 20. So if the acetaldehyde comes through here and it touches that condenser, 30 degrees is 10 degrees above its boiling point. It'll vaporize it, you know what I mean? It's not going to condense it. But the ethanol, it condenses at 78 Celsius, say 80 degrees. That's a 50-degree difference. So it will condense all the ethanol out, and you can see I have a set funnel. There's the little handle, and the ethanol will collect in there. But the acetaldehyde, the ethanol that does react and makes acetaldehyde, it'll come up through here and condense, come down into this round bottom flask that has an ice bath there. Now when this fills up, because a lot of the vapor isn't going to react, so I'll have a lot being condensed in here. When this starts emptying out, I can always open this valve, and I have a hose connected here, and there's a valve on this too, so I can open this valve, because otherwise I'd be distilling stuff up inside there. So I open up the valve here, I open up the valve here, the stuff trickles down into the pot, and then I can close the two valves up so that I can start collecting some more again, and so I don't distill stuff through this tube. This is the temperature you need the copper to be at to do this reaction, 260 to 290 C. And you can see the equation. You're just basically taking the hydrogen off here and the hydrogen off of this carbon, and then you have an H2, which is gas, and you have your acetaldehyde. You make a double bond, right? You took two hydrogens off. Now, so far what I've been talking about is one source of information, and it has this as the equation that I just showed you. And this is the degrees that you would go with the reaction. But another source that's about copper oxide, you know, how to make copper oxide by heating it, says you need to heat it between 300 and 800 degrees C. And I was under the impression that that's what happens. You know, and it says copper here as a catalyst because it keeps recycling or whatever. But so I'm probably going to do this reaction at 350 C just to make sure that I'm, you know, in range. If you use silver instead of copper, it's about 560 C. But my whole point here is this. I don't know, because this is such a generic equation and I don't like this being low like that. I'm unsure what the deal is, but if it is copper oxide that you're making, CuO, right? Here's the equation for the last thing that we've been talking about so far, right? It'd be copper oxide. You change the alcohol into a aldehyde and you end up with hydrogen, right? The thing is what about this O? Like, look at this first equation. This O, the way I figure it out would be you'd make H2O. The H2 would come from the hydrogen that you made, and the O would come from here, this copper oxide. And now you have copper instead of copper oxide. Or is it that the copper oxide does make the hydrogen, and the oxygen comes together, and you get two of them, to make an oxygen. You're making hydrogen and oxygen, not water. So I don't know which one of these is true. And then, of course, you have copper. Are you making hydrogen or are you making water? And if you're making hydrogen, what happens to the oxygen over here? Where does it go? You know what I'm saying? Or you could be making both, maybe. You could be making H2 and water. You know what I mean? I could have done another equation. But if you are making hydrogen, a point I want to make is that copper oxide and hydrogen, if you heated it, right, delta T, you would reduce it back to copper and make water. So if you're doing this, this hydrogen that you make will be trying to reduce the copper oxide to copper instead of what you want, which is the alcohol to reduce the copper oxide to copper. That way you get aldehyde, which is your product, right? You don't want any competing thing trying to use up that copper oxide. That's what's oxidizing your alcohol. So anyways, I'm not sure which one of these is right. I don't have any with me right now, but I did buy some of this quartz glass, but it's like a cotton, like a fiberglass, you know, like that insulation you put in your house. But it's quartz glass, right? I'm going to call it quartz cotton. Basically what I'm going to do is I'm going to get some copper sulfate, put it in water, let it dissolve, right? Because I don't have any copper. I mean, no copper powder. And silver works with this too. You can use silver, which I may do also, and I have silver nitrate already that I made in the video. I can have the solution be silver nitrate. Then I throw in my quartz cotton, and I do have iron powder. I'll add that to the solution, and I'll stir it up, you know, and all those iron will go into solution, and the copper will come out of solution because the iron is more reactive. So then I'll have iron sulfate, or in this case, iron nitrate. And the copper or the silver will precipitate out into little fine, which is what I want, little fine particles. I don't want a chunk. Then I stir it so it gets all, you know, and I pull the cotton apart so that, you know, it's all nice and meshed out. And then I can stir it, and the particles of metal will cling to that cotton, that quartz cotton. Take it out and wash it with water to get the, you know, whatever salt water you have. You know, if you're using copper sulfate, you're going to have iron sulfate salt in that solution now, you know what I mean, when the iron goes into solution. So you want to wash that off and let it dry, and then form the cotton, you know, because you're going to put it into this tube, right? Form it into, you know, the size, you know, the inner diameter of that tube. then heat it with a torch. Don't heat it so it melts into one solid chunk, but heat it so it fuses the copper into the cotton a little bit, you know what I mean? And then I can slide it into that tube and just let it kind of sit there while I'm heating it up. But that way the little particles are dispersed more evenly, and they're more small, more surface area. And the more surface area, the better. And you can see from my last video that I did put, I had some copper sulfate solution, and I put some iron, some steel wool in, which steel wool is just iron with maybe a little bit, a couple percent of carbon in with it too. So it was mainly iron. I threw the iron in, and you can see immediately, as soon as I threw the steel wool in, the iron in the steel wool turned all shiny copper like, you know what I mean? And then you stir it up, and it heats up, and so that's an example of a displacement reaction, because the copper is not reactive at all. It's like gold or silver. It's not reactive. The iron, on the other hand, is reactive. So if you put them together, who's going to want to react with the cation? I mean the anion. Obviously, the iron is, it's more reactive. It's going to want to react. Copper doesn't want to react. It wants to stay copper. Just like silver wants to stay silver and gold wants to stay gold. So the iron goes into solution as an ion, a cation, and the copper comes out of solution. And this is the same with silvers. If you have silver nitrate, the silver wants to come out of solution because it wants to be silver. Whereas the iron is more reactive, so it wants to react and become a cation. As will the air pump. Remember I said I was going to put an air pump in there to help circulate the vapor, the ethanol vapor, and help oxidize the copper oxide, right? Because that's what does the oxidation, the copper oxide, not the copper. That's why you heat the copper. You heat the copper, it heats so much that it turns into copper oxide. But once you use up all the oxygen, I'm thinking, you're going to need more oxygen, you know what I mean? Because when it oxidizes the ethanol to acetaldehyde, it gets reduced, right, back to copper. So you're going to need oxygen to redo, this is to recycle this reaction, I would think. It may hurt by oxidizing the acetaldehyde to acetic acid. Aldehydes are very easily oxidized. Even oxygen in the air will oxidize, the aldehyde into the acid. So I think the thing with the airflow on the air pump is that have it be enough to displace all the hydrogen so it doesn't react with the copper oxide. Also have it be enough to make copper oxide, to replenish the reaction, and have it be not too much that you over-oxidize the aldehyde into the carboxylic acid. I think there's a fine line on how much to give it and how much pressure and how much, etc., etc. Instead of putting the ethanol in, we put in methanol, right? And instead of this condenser, because you're not going to be able to condense the formaldehyde out, you would just have a hose up here that runs into some water so you can make formalin. And you just have to ice it down. Maybe I'd get some dry ice or something so I can have a lower temperature than 0 to really make sure I can keep the formaldehyde in solution. In some reactions you need dry formaldehyde, so if this worked, and I could get the water and the ethanol out by using this condenser, before the hose, it can just be, you take the hose to your reaction, whatever you're reacting it with, and maybe send it through a drying agent like magnesium sulfate or something like that. So as you can see, I'm not 100% sure about anything on this reaction except that it works. So if you have any suggestions or you think I can do something better or different, please post, let me know. But anyways, you all have a great day, and always remember, science is great.